Hey folks, this next video is on apparent weight. Apparent weight is something that is specific to the normal force, and it's something that we'll come back to when we study circular motion. Apparent weight is really just code for the normal force. The idea behind apparent weight is that sometimes it matches up with your actual weight. So could be equal to mg, it could be greater than or less than mg. So it's normal force, and you're gonna compare it to the value of the weight of an object. And so the idea behind apparent weight is, depending on what you are doing, you could feel lighter or heavier than you are. The extreme version of apparent weight would be when you feel weightlessness, and so I'll have you maybe think about that during class. But we're going to focus on apparent weight in an elevator. Again, you'll probably, once we go through this, be able to think of like other situations where you felt this change in apparent weight, but we focus on elevators. So I have drawn like a crude version of an elevator shaft. So these, like, here's the elevator. Here I am standing inside. There's like rollers on the side to, help the elevator like roll up the elevator shaft. There's a bunch of cables, and it's attached to a pulley that either you can or can't see if you're like standing on top of the elevator. Maybe there's another elevator tied to it. At the very least, there's like a weight on the other end that's basically equal to the weight of the elevator. We'll talk about that some other time. But, we'll say we're on the ground floor, and we're going to get in the ground floor, and we're going to travel up the elevator. So riding up an elevator. And so what I want you to think about is, assuming you've been in an elevator, there aren't many that you might use regularly nowadays with COVID, but you've probably ridden in an elevator. And what you want to notice or want to remember is that when you get in an elevator on the ground floor and the elevator starts to move, there's this like little feeling of being heavier, as if you're getting pushed down into the floor of the elevator. And that should make sense, because there's this force of the cables that's lifting up the elevator. And so the elevator starts to move, and your body, Newton's first law says, your body just stays there until a net force is acted on it. And so that net force comes from the elevator itself, the elevator floor. So the elevator starts to move, and then your like inertia causes you to kind of lag behind. And so you accelerate with the elevator. On the ride up, things feel kind of normal. This is especially true of like long elevator rides, but things feel kind of normal. You feel like everything's like as usual in your body. And then when you get to the top of your elevator ride and the elevator starts to slow down, you have this like feeling of weightlessness. You feel lighter than normal. And so we're just going to kind of examine that. And so we're going to start with our usual like free body diagram. And it is very simple in this situation. There is the normal force pointed up, and there's the gravity force pointed down. And so I'm just going to write one little equation, and we'll talk about all the different situations in an elevator that cause your apparent weight to change. So there are no x forces. And so I'm going to write out just in the y direction. And arbitrarily, not arbitrarily, we're going to assume that up is the positive direction. And so we're going to say normal force minus mg equals ma. And so that's going to be your vertical acceleration. Normal force minus your weight equals your mass times the acceleration of the elevator. If I solve this for normal force, I get the sum of the acceleration of the elevator and the value of little g. So this is specific to an elevator or any other situation that mimics an elevator. And so there's basically like three things that can happen. It's just a matter of like figuring out what is happening. And so what we want to analyze qualitatively is a velocity versus time graph. And I'm going to draw this like this, so that you can see kind of the entire ride of an elevator. So positive and negative. This is velocity, this is time. So if we think about, let's say like a round trip on an elevator. You stand in the elevator and the initial velocity of the elevator is 0. And then the elevator is going to move up. When the elevator moves up, the velocity gets more positive. And so we have a line that looks like this. After a pretty short amount of time, that line flattens. And that's kind of the middle of your journey. When you get to the top of your ride, the elevator has to slow back down. And so we get back to a velocity of 0. And then some amount of time passes where the elevator's like letting people off. Let's say you're just there to ride the elevator that day. So you you rode it up to the top floor, and then now you're going to ride it down back to the bottom floor. And so the elevator is going to start and it's going to accelerate to get the elevator moving downward. And so we have that type of shape. The ride down looks like that. And then to slow the elevator down looks like this. So, just to kind of remind you of what's happening, this is the ground floor, and this is the top floor, and then this is where you get back to the ground floor again. And so all I want to point out is that this is the shape of like an elevator ride if you rode from the ground floor all the way up to some higher floor and then back down. And the way this plays into Newton's second law is these are slanted lines on a velocity graph. And so positive acceleration is what you experience here, and it's also what you experience there. And you will notice that those are the two lines that happen very close to the ground. That's either when the elevator is accelerating to move upward, or when the elevator is decelerating to get to the ground floor. In that situation, if acceleration is positive, then according to this expression, normal force is the sum of two positive numbers times mass. And that means that the normal force is going to be greater than the weight of the object in the elevator. So that's if you have positive acceleration. Positive acceleration tends to happen, or does happen, at the bottom of an elevator ride. Conversely, near the top, this line indicates negative acceleration, as does this line. And so if you have negative acceleration, then you have, so m times a plus g. So negative number plus positive number, that essentially is the difference between two numbers, a big positive number, and then usually a small negative number. And you get this expression to spit out the idea that the normal force is going to be less than the weight of the object. And so again, toward the top of an elevator ride, this is what happens. Slowing down the elevator on the way up, or speeding up the elevator on the way down, both result in a feeling of like temporary weightlessness, because the normal force is, sorry, I didn't move down, because the normal force is smaller. So if the acceleration is positive, you feel heavier. If the acceleration is negative, you feel lighter. Positive and negative really are just codes for accelerating up versus down. And so please stick to the positive versus negative, because it actually doesn't mean that the elevator is moving up or down. It means that the acceleration is positive, right? So this is positive acceleration moving up, but this is positive acceleration moving down. Last but not least, if acceleration equals 0, well, that is any flat line on a velocity graph. So that would be the middle of a ride. As the velocity of the elevator has stabilized, which if it's a good elevator, it's stabilized, the acceleration equals 0, then the normal force is equal to the weight of the object in the elevator. So for objects in elevators, the apparent weight of those objects changes based on what the elevator is doing. So the elevator exerts a force on the person riding the elevator, and it can't change their weight, but it can change how heavy they feel based on what the elevator is doing. And that is that for now.